Okay, so in chapter 6, we're going to get to something that engineering statics is kind of, if it's famous for anything, this is what it's famous for, which is a lot of times people say, well, what is engineering statics all about? And it's like, well, usually you say something like designing bridges or something, and they go, oh, okay. So anyway, so this is the closest to that sort of thing we're going to have. And it has to do with what we call truss analysis. Okay. And what you're looking at here in our picture is a super primitive truss. Now, you've seen lots of trusses before. Um, so, for example, if you look at, let's say, um, an antenna mounted up really high, okay, you can have some stuff going on. And then you've got this sort of structure in here like this. All right, maybe you got something going on kind of like that. Okay. Those are trusses. Okay. So trusses are just it's a reinforcing structure um to help achieve whatever you want it to be, whether you're going to put an antenna up here or maybe it's a fire lookout or who knows what it is. Okay. It could be there. It could be something that is like with a bridge. If it's with the bridge, then we turn it sideways, like that, and then cars can drive across this thing. Okay, but anyway, that's a truss. Okay, and like I said, what we're looking at here is one of the most simple trusses ever. Okay, now, our job in doing this analysis is to figure out what's going on with the beams, okay, with the individual components of that truss. All right, so let's take a look, for example, at this piece right here. Okay, so we'll call it AD, so piece AD. And what we'd like to know is piece AD, is it under tension or is it under compression? Okay. So if it's under tension, then that means what's happening to it is that it's getting pulled apart. Okay. So imagine it's like a spring and it's going to try to stretch. Okay. Now let's flip our perspective. What does a stretched spring do? A stretched spring pulls, whoops, pulls in opposite directions. So if this thing were, I tell you what, let's color code this baby. If it was under tension, then that means up here at the top, it's going to be pulling down, and here at the bottom, it's going to be pulling up. Okay. Now, on the other hand, if it's under compression, oops, what did I do? There we go. If it's under compression, then that means something's squeezing it. So if it's like a spring, something was trying to compress it. Okay. And what does a compressed spring do? A compressed spring pushes back. So if it's under compression, that means it's pushing on the ends this way. Okay. So we're interested, is the beam being stretched, tried to stretch, or tried to compress? Okay. Which is the same thing as asking, is the beam pulling on the ends or pushing on the ends? All right. Those are the same things. So you might want to think about that for a few minutes. Make sure you've got your head around that completely. Okay. Now let's talk about what's happening at the joints. Okay. So A, B, C, D, those are the joints. Those were the two pieces to come together. And I've kind of mentioned this before. These joints are what we call pin joints. So AB has got a hole in it and DC has got a hole in it. Okay. And they fit together just by that pin. Okay. So sort of imagine a rivet or something like that going in there. Now, the pin cannot pass any moment. Okay. So all you need to think of all these joints as being floppy. Okay, they could all flop around. And so we've got to have all this structure around them so they don't flop apart. So they maintain the shape that we want them to have. Okay. Okay, so there are two ways to do this kind of structural analysis. Okay, this kind of analysis on our truss. Okay, and the two kinds are um, what we're going to do today, which is called, whoa, which is called the method of joints. And the other method is called, we'll do this later, the method of sections. Okay. Now, I'm not going to talk about the method of sections because we're going to get to that. All right. But you need to know that there's two ways to do these. On your next test, I will give you a particular truss structure, and your task will be to analyze it using both methods. Okay. You need to be able to show proficiency in both methods. Now, the upside of this is that you should get the same answers. Okay. What I want to know is, can you get the answers? Do you know how to do it both ways? Okay. In the real world, you could choose. Sometimes one method is easier. Sometimes the other method is easier. Okay. It just depends on what you need, what your situation is, all that sort of thing. Okay. All right. So let's get into it now. I'm going to have to erase a bunch of stuff. Let me just make sure that I've hit all the major intro stuff here. Okay. All right. So no matter which method we use, we really need to start by thinking about what's happening with the external forces. Okay. Now, in this particular case here, there's an applied external force, which is this 450 right here. Oh, hang on just a second. Let me get rid of some of this stuff. It's going to get messy in a hurry. I don't want to do that to you. Boom, boom, boom. Okay, there we go. What I was saying was, no matter what your method that you're using, you need to begin with the external forces. Okay. Now, our external forces, we've got that 450 right there. Okay, there's an external force. Um, it's an applied external force. Okay, so it's an applied external force. The other external forces that we're going to have are reactive external forces. So, in other words, that's what the supports are doing. Okay, so we have an applied external force at D, but we're going to have a reactive force from the supports at A and C. Okay, nothing from the outside touches B. All right, so when we think about the external forces, we don't deal with D at all. Okay, in fact, when we get ready to think about our external forces, we basically want to think about this thing as a big triangle. Okay. We don't care about anything that's inside there. Hash mark it to death. Okay. So we've got this triangle and we want to know what's happening to the triangle. Okay. And the thing that's happening to the triangle is we have an applied external force and then we have reactive external forces. Here at A, it's a roller bearing. Okay. So to me, it looks like a little roller skates on that thing. Okay. So it could go back and forth. Uh, but the point is that A can only provide a normal force. Okay. Now let's go over here and look at C. At C, okay, it's a pin. And what we want to do with most of our pin joints is Well, let's back it off just a little bit. But so the floor where we're mounted in there is we're going to say that there's a horizontal component to its reaction and there's a vertical component to its reaction, just like this. Okay. Boom, boom. Okay, so we're going to have to find A, CY, and CX, just like that. Okay. All righty. Now, you want to think about these things carefully. Okay. And, take your time as you get started. So, CX and the 450 are my only horizontal forces, right? That's all I've got for horizontally. So that means that CX is going to have to be equal to D. Okay, so I want to write that down. Oops, let's write that down. CX is equal to D. Oh man, I am struggling today. CX is D. Okay, just like that. Okay, so we got that taken care of. Now, let's think about A and CY. They're both vertical. And we got a problem. How is this thing going to be in equilibrium if A and CY are both up? There's no downward force. So that would mean this truss would just be like, pew! Okay, it would just take off. Okay. And then that makes it a dynamics problem, which we have to deal with next semester. So that means A and CY, since they're the only vertical forces, they actually have to be equal and opposite. So let me get my eraser here. And this guy here is in there wrong. Okay. It's actually going to have to be this way. So there's that. Now, we can see right away that A and CY, I said it already, they have to be equal and opposite. Okay. So let's write that down. So A is equal to CY. Okay, so I got that. But that doesn't help us get either A or CY. Okay. Now, you guys have enough experience that um, what I've just done is I summed the horizontal forces equal to 0, and I summed the vertical forces equal to 0. Okay. So what's my other option? Moments. Okay. So I need to look at the moments. Okay, and what we'll do is let's put a pivot here. Okay, and so then from my 450 up here, then that's going to be a positive moment. So that's going to tell me I've got 4 times 450. Okay, and then my negative moment, I got nothing from CX or CY, so I only have A to deal with, and A is out there a distance of 8. It's negative, so I got minus 8A is equal to 0, and so we see then that A is gonna be 225. Okay, since A is 225, then CY is 225, and CX, by the way, is 450 because it's the same thing as this guy right here. Okay, so far so good. All right, we've got all of our external forces. So getting back to the two methods, method of joints, method of trusses, method of joints, method of sections. No matter which one we do, we have to start here, okay? Identify all the external forces. What are the applied and what are the reactive external forces? Get all those first. Now, we've done the outside of the structure. Now we begin to move to the inside of the structure. Okay. Now, in order to treat the inside of the structure, then what we'll do is we're just going to focus on this joint right here. Okay. So, what I want to do is I want to draw a free body diagram for that joint. Okay. So this is for A. Now we know we have the force up A, just like that. Okay. That's the only thing we know so far. Now that joint has to be in equilibrium. And I'm saying joint, but if it's helpful to think about the pin itself, then that's fine. Okay, so what else is happening to the pin? Well, we know that we've got a beam right here, and that beam is going to push or pull on my pin. And we know we've got a beam right here, and that beam is going to push or pull. Okay, so how do you figure out if it's pushing or pulling on the pin? Well, um, it's one of those things where you really have to do it a bunch of times. Then you begin to get a feel for it. Okay. But if you don't have a feel for it, here's how you do it. Okay. Okay. So I'm going to use yellow here because what I need in my free body diagram is I need to be able to represent the direction of what's happening with the beam AD. Okay. And so what I'm going to do is I'm going to draw a line right here. And that line represents the direction for AD. Now, what I don't know is it going, do I draw my force arrow this way or this way? Okay. So here's how I figure that out. A is up. AB is going to be in this other direction this way. Okay. So that means that AD really is going to have to take care of the horizontal part of B and take care of A. And the only way that can happen is if AD is down this direction. So there's AD. Okay. Now you see AD has a vertical component, and I can set that vertical component equal to A. Okay. And let's go ahead and take care of that while we're doing it. All right. So that's going to be, let's call this angle theta right there. So we're going to say that AD sine theta is going to have to be equal to A. Okay. Now we already know that A is 225. And so that means that AD, that's a 45-degree angle, by the way. Okay, let me pulled way down there. Okay, there's our angle right there. And this is 4, and this is 4. So I've got an isosceles triangle there with 45-degree angles. And anyway, once you carry out the math, put in sine 45, what you get is 318.2. So that's what we got for AD. Okay. And we figured out its direction. Okay. So now let's figure out what's going on with the beam AB. So the one going across the bottom there. Okay. And so is it going to have to push on the pin or pull on the pin? All right. Well, we know that AD is pushing on the pin, and as AD pushes down and to the left, it's got a leftward component. That means we have to counteract that leftward component. And so this is what we get right here for AB. Okay. That's how we get AB out of this thing. And then what we can do is we can just come in down here and say that AB is going to have to be AD cosine theta. It's 45 degrees. Anyway, so it's going to be the same thing as A 225. Okay, alternately, we could have said that tangent of theta has to be equal to A over AB. Okay, so a couple of approaches we could we could take there. Either one is going to work just fine. But we have figured out AB and we have figured out AD. Okay, so let's come up here and let me get rid of some stuff. It's going to get a little messy. We don't want that. All right, but we have figured out this beam and this beam. Okay, so we got 1, 2, 3, 3 beams left to take care of. All right, so let's move, and we're doing the method of joints. All right, so we did a free body diagram at A. Now we have to do a free body diagram at B. Okay, so the strategy here is once we fully understand one joint, move to a nearby joint. So we've got some information to work with. Okay, so let's move to B. All right, so we're going to make a free body diagram for B. All right. Now let me draw in what's happening with AB and AD at A. So AB is here and AD was, whoops, I did that again. Okay. AD was here. Okay. Try to erase a little dot there. Okay. These things can get really messy if you haven't already figured out. So let's move over to B. Okay. AB itself, the beam, has to be in equilibrium. And so that means over at the other end, AB, we'd draw in that way. Okay. So think about this AB like a spring. Okay. How can it make a force at A in the direction that it does? So here's A, it's something's going this way. That means it's tugging on A. It's tugging on A. So that means it's like a spring that has been stretched. That means it's going to tug both directions. Okay. So it pulls in on A and it pulls in on B both. And it pulls in the same amount. Okay. Pulls in the same amount. AD has something similar happening in that up at D, which we're not ready to talk about D yet, but just while we're on this topic here, AD is like it's being compressed because it's pushing out. Let me do it this way. It's pushing out. So it's pushing on A. So it's got to push on D. So however much it's pushing on A, it pushes on D the same amount. All right. And that equal and opposite idea is something we're going to have for every beam that we run into. Okay. Once you figure out what it's doing at one joint, just flip it around for the next joint. Okay. And it works out just great. So back to B. We know all that was to say that we know what's happening here. There's AB, just like that. Okay. And we've got the beam BC over there on that side. And it's going to have to be equal. Oops. It's going to have to be equal and opposite here, like this. Okay. Because they're perfectly lined up with each other, right? Okay, so they have to be equal and opposite. So we can draw in up here. Here's BC. Okay, and that means over here at C, it's going to be this way. Because again, at the other end, it's doing the same thing but backwards, but reversed. All right. So now let's talk about I need a new color here. This guy. Okay, so that is BD, is what that is. Okay, so does BD push or pull on this thing? Well, we don't really know right off the bat. Let's assume that it's going to push on B, which means it's going to be down. Okay, that means in my free body diagram here, I'm going to have this. Okay, but if you look at that free body diagram, it is not in equilibrium vertically. Horizontally, we said it's in equilibrium, but vertically it is not. There's nothing to counteract BD. There's nothing to counteract that blue beam that I drew, okay? And the only thing that we conclude for that, if we were to go through the algebra, it would be a waste of our time, but we're going to figure out that BD is equal to 0, okay? So we can't have that, which means we can't have that either, okay? And we learned then that BD is 0. Okay, and we learned that BC was 225 because it's equal to AB. Okay. I still got to put some money in my PayPal account. I intend to do it, but then I got to link my bank account to my PayPal and I got a routing number, blah, 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 blah. Anyway, you guys know how that goes. Okay. There we go. So now we've got this guy, BC, and BD, we said is equal to 0. Now, I want to talk just a little bit about BD, just a little bit more, okay? Because there is a pattern. Okay, let me see if I can just get rid of some of this highlighting. Okay, there's a pattern here. And when you see this pattern, you know you've got what we call officially a zero force member, okay, which means it doesn't do anything in terms of it doesn't do anything for our external applied force, okay? It doesn't do anything for that. Now the pattern there is that you've got to have two beams that come together to form a straight line. It's got to be perfectly straight. If it has any kink in it at all bets are off. But if it's a nice straight line coming across like this, then that means they're either both pushing or they're both pulling. Either way, they're equal and opposite. They cancel each other out. And then there's not going to be anything to cancel. Ooh, sorry about that. There's not going to be anything to cancel whatever else might be happening with a third beam. Okay. So you're pretty much only going to get, well, I don't want to say this is only going to happen when you have three beams that come together because there's other things could come into play. But if you've got three beams like this and you can eliminate one of them by seeing that the other two form a straight line, great. You've saved yourself quite a bit of time. See, we didn't really need to do the whole join at B at all. I only did it to show you that there's such a thing as a zero force member and how cool it is. And if you get to see it, give yourself a little fist pump. Okay. Pump, bump. You can bump your own fist if you want to. Okay. All right. So let me get rid of those things. Boom, boom, boom. So zero force members are our friends. Okay. All right. Let's see where we are. We got all our external forces. We got AD. We got AB. We got BC. We got BD. There's only one left, DC. So let's jump over. We could do D, joint D, or we could do joint C. It doesn't matter. It doesn't matter. Okay. We don't have to do them both. We can just do one. I went from A to B. I'm just going to jump to C because it's alphabetical. Okay. That's the only reason for that. Okay. So what we do again is at joint C, we're going to make a free body diagram. Okay. And then we're going to put in what we know. And what we know is we've got CY down. We know that. We know CX is this way. We know that. And we know that BC is this way. We know that. Okay. Now, BC happens to be 225. Okay. So that's BC. And CX happens to be, we got that somewhere. CX. Oh, there it is, 450. Okay, so that's 450. Okay, now I'm going to go ahead and write that this is BC and this guy is CX. And CY, okay? But I wanted you to see horizontally, we're not in balance, okay? We're not in balance. Things are tilted to the right in terms of magnitudes of force, okay? Now, let's go ahead and put in, like we did before, our direction for the unknown beam, which is DC. So that direction is going to be here, okay? So it's either going to go up and away that way or down and away this way, okay? Um, CY alone gives it away because we need something going upwards. We need something with an upward component to take care of that. And so we're going to put it, oops, wrong thing. Okay. We're going to put it in here just like that. So there's CD like that. Okay. It's still a 45-degree angle in there. We know that. Okay. And so what we can do is we could just say that we've got CD times the sine of 45, and that has to be equal to CY. And when we work that out, we're going to get the same number, 318.2. Okay. Just like that. Okay. Let's see if I can get everything in there now. Okay. So now we've got all the beams worked out. All right. So I want to kind of step back, help you understand strategy. How do you approach these things? Okay. So the first thing you do is you ignore all the inside bits. Okay. Treat it like it's a solid object. So in this case, treat it like it's a solid triangle. Then you want to say, what are my external applied? What's my applied external forces and what are my reactive external forces? So here we did the 450. Okay. And we knew A had to be up. We knew CX had to be off to the right. We knew CY. Initially, we guessed up, and then they were like, wait a minute, that doesn't work with A. So we turned it around just like that. Okay. Then we treat that solid triangle, treat the solid object as an equilibrium object where you're going to have to sum the vertical forces, sum the horizontal forces, and sum the moments. And that's how you're going to nail down all of your reactive forces. What's happening at A, what's happening at C. Okay. At that point, now we're ready to zoom in, we're ready to go inside, pick a joint. Okay. My recommendation is pick a simple joint. That's why I started at A. There's only 3 things happening at A. Okay. We're going to make a free body diagram at A. And then we drew in the directions for AB, which was horizontal, and the directions for AD, which was in here like this. So that could help us figure out what's pushing and what's pulling. All right. Then that particular pin at A must be in equilibrium. So we sum the forces vertically and horizontally. All right. It's a single point. We're not going to deal with any moments when we've got just a single point. Okay. Once you know everything about one joint, move to a neighboring joint, do it. Move to a neighboring joint, do the next one. Okay. So, like I've said many times, take your time. Okay. Try to be orderly and neat with your work. That's going to save you a big headache. Okay. Messy paper, messy mind. Keep things nice and orderly. All right. There we go. We're going to look at some more examples in the next few videos.